Since the early years of fiber optics, there's been a need to passively switch, tap, split, and multiplex optical signals. Today's technology allows designers to expand on these original tasks by also providing the ability to direct, control, and filter optical signals for use in more creative and cost-effective system designs using innovative passive devices. In fiber optics, the word passive refers to those devices that do not require electrical to optical or optical to electrical conversion during its operation. Passive components include simple optical connectors, splices, and fixed optical attenuators, but also refers to more complicated, electronically controlled optical devices like switches and variable optical attenuators. From the very beginning, the need to monitor optical signals in laboratories was critical when measuring or analyzing performance. The balance between laboratory, manufacturing testing, and field testing drove the fiber industry to develop products allowing greater flexibility. As fiber optic communication systems expanded from conventional point-to-point networks, the need to split, tap, and attenuate signals resulted in products with better specifications, better environmental performance, and physical durability while decreasing component size and costs. In the case of CATV networks, the use of optical splitters allowed for broadcasting of video signals to thousands of subscribers through the hybrid fiber coax systems. Splitters are also known as couplers and have a number of characteristics that determine their function and application. These include the number of input and output ports, signal attenuation, the directionality of the light transmission, wavelength selectivity, single or multimode operation, as well as the polarization sensitivity and the polarization-dependent loss of the device. In the early days, the only passive components available were simple optical splitters and attenuators, which used internal filters to change attenuation values. But as optical technology matured, wavelength-specific components emerged, leading to advances such as wavelength division multiplexing, which vastly increased the data capacity of optical networks. Wavelength division multiplexing combines a number of optical channels into a transmitting fiber, with each channel transmitted at a different wavelength. Early terrestrial systems operated over multimode fibers with dual wavelength division multiplexing, or WDM, at 850 and 1300 nanometers, using wide spectral width LEDs. Later, these systems migrated to single-mode fibers, using laser sources operating at 1310 and 1550 nanometers. WDM systems would not be possible without a range of wavelength-dependent passive components, and as the technology grew, these products would lead to the communications explosion from long-haul oceanic and even fiber-to-the-home installations. The impact of oceanic or submarine fiber optic systems cannot be overstressed when discussing passive optical components. Due to the small numbers of fibers used in oceanic systems, the need to increase the capacity of these fiber-poor cables required the addition of optical multiplexing to the existing electrical-based time division multiplexing schemes. Multiplexing numerous laser signals with smaller spectral widths enabled submarine systems to operate at terabit rates when previously they had been limited to only tens or hundreds of gigabits per second. In the 1990s, this expanded multiplexing capability came from a surge of new technologies, all influencing each other. Low-loss single-mode fibers operating at 1550 nanometers with losses in the 0.2 dB per kilometer range allowed for longer spans without regeneration of the optical signal. Simultaneously, intense research and experimentation led to the development of the erbium-doped fiber amplifier, or EDFA, and incorporated optical couplers, isolators, filters, and WDMs. The EDFA was unique in that it could optically amplify all wavelengths across an optical spectrum. As manufacturers began to produce lasers with tighter spectral widths, dense wavelength division multiplexing, known as DWDM, having optical spacings into the tenths of nanometers became a reality. This required optical filters to demultiplex these wavelengths. Another key requirement in DWDM systems was to prevent the optical drifting of the laser light sources. Wavelength lockers presented a solution to this problem. At the same time, optical isolators were being integrated into the optical subassemblies of high-speed systems and optical amplifiers due to the increased effects of reflections on laser and system performance. Combined with new optical fibers, the EDFA, and an explosive communications revolution, These technologies would drive optical multiplexing into point-to-point, long-haul networks, and eventually into metropolitan area networks. These networks use DWDM in ring architectures, which required an optical solution to add and drop wavelengths at multiple access points throughout the physical ring. The fiber Bragg grating provided the ability to filter specific wavelengths, and when integrated with the optical circulator, would provide the add-drop function. Other passive products evolved for use in WDM, including the interleaver. Unlike other demultiplexers, the interleaver uses light interference in a fiber structure to split a group of evenly spaced optical channels into sets of odd and even channels. These channel subsets have wider channel spacings and can be more easily processed by components not requiring such tight tolerances. The implementation of DWDM technology in the 1990s to the present allowed for the fiber industry to manufacture products at a lower cost with greater reliability. This in turn would provide the passive and active components required to fulfill the vision designers have had for decades of building all optical networks. Another type of WDM, known as coarse wavelength division multiplexing, or CWDM, used 20 nanometer spacings, allowing greater flexibility of components at a reduced cost. Long-haul systems push the limits of technology and reliability, but providing fiber to the home has always been a goal of the fiber industry. In 1998, the International Telecommunications Union released the ITU-T G.983 Broadband Optical Access System Standard, based on the Passive Optical Network, or PON, to address a low-cost option of delivering bidirectional communications to the home and business over a single fiber. The PON solution was actually quite simple, using the standard CATV architecture, low-cost active and passive components, along with established ATM and Ethernet protocols. Optical splitters would be located in the outside plant to allow a single light source to send signals to multiple homes and businesses. The emergence of devices that integrated active components such as lasers and photodiodes, along with WDMs and filters into packages called diplexers and triplexers, allowed for the transmission of bidirectional voice, video, and data signals over 2 or 3 wavelengths between the service providers and the subscribers. The ITU standard specified the optical wavelengths, attenuation, reflection, and dispersion values required using the ITU standardized G.652 single-mode fiber. By using standardized products originally developed for DWDM, the PON network design reduces the installation and operating costs by eliminating active components between the transmitting terminal and the subscriber. Future versions of FTTx PON will incorporate other passive optical devices to expand the capabilities of the network. The use of optical switches at fiber distribution hubs in the outside plant allow for easy reconfiguring of the network, while the option of assigning each user their own wavelength through DWDM technology has already been demonstrated. While PON continues to increase the bandwidth capabilities for the home, this increase must also be supported in the local loop, metropolitan, and long-haul networks. In these applications, the use of optical switches, filters, gratings along with reconfigurable optical add-drop multiplexers, or ROADMs, will be optimized. ROADMs will be used in the next phase of optical communications, incorporating new variations of optical switches. Simple 1x2 electronic optical switches have been around for decades, allowing easy switching between light sources operating at different wavelengths. In 1987, the Fiber Distributed Data Interface, or FDDI standard, was the first standard to incorporate optical bypass switches to maintain reliability should one fiber, connector, or card fail. The term route redundancy became the driving force behind optical switching evolution, along with the increased speed and efficiency of the networks, with reconfigurations occurring in the milliseconds. Optical switches improved with each newly developed state-of-the-art technology. Terms like optical electrical optical, or OEO, optical cross-connect, or OXO, and optical optical optical, or OOO, became common descriptions used to describe optical switches. Optical switches grew with the technology, with switches handling fiber counts up to 1,000 ports using a variety of techniques. Key elements of the optical add-drop multiplexer, or OADM, are the optical circulator and the fiber Bragg grating. These components allow switching of wavelengths by adding and dropping them through the optical ports with no fiber movement. The development of the ROADM, or Reconfigurable OADM, now incorporates MEMS technologies, resulting in equipment with a very small footprint. Power requirement for MEMS devices are also very small, reducing operating costs. Placing ROADMs in remote switching cabinets and into FTTx networks will provide the remote switching capability to supply customer wavelengths, network testing, protection, and route redundancy. In 2003, the ITU released the G.709 standard titled Optical Transport Network, or OTM. This standard is designed for high-speed services including 10 and 40 gigabit systems, but also ROADM networks, which enable the routing of the high-speed systems. From a provider's perspective, the addition of optical switches also allows the network to be reconfigured from remote sites in response to the changing bandwidth needs of the individual network. Optical switches can also be used to dynamically route a variety of data, audio, and video signals to different locations in applications such as video conferencing, intelligent transportation systems, and many others. Earlier, we saw how the EDFA addressed the attenuation issue, but at high speeds and with alternate routing of a span, the problem of optical dispersion caused by the laser, the optical fiber, and differing physical lengths also needs to be addressed. History has shown that when an optical problem surfaces, optical solutions are developed to resolve the problem. An example of this is four-wave mixing in dispersion-shifted fiber. This problem was resolved by the development of non-zero dispersion-shifted fibers in the early 1990s, which led to the DWDM explosion. A more recent example includes the optical dispersion compensator, which is designed to provide a solution to dispersion problems in high-speed and long-distance installations. Another important consideration in reconfigurable networks is active dispersion management. When switching high-speed multi-wavelength signals among fiber spans of different lengths, dispersion compensation must be tailored to the individual span. Optical switching systems can be used to switch in the correct amount of dispersion compensation as needed. Passive components have created innovative opportunities for entirely new ways of handling multi-wavelength optical signals. In the following chapters of this program, we will look more closely at these critically important devices and how they have impacted and influenced optical communications.